Okay, so far we have defined derivatives and looked at different ways of thinking about them, but we have not computed a single derivative. So let's remedy that, and let's start by looking at the simplest thing whose derivative we can take, other than, I guess, the zero function. But this would be an example of the simplest thing. How about a linear map itself? So let's say A is a linear map, meaning A maps Rn to Rm and is linear. Then I'm going to claim that A is everywhere differentiable in its entire domain. So here I'm going to think, when I'm talking about the derivatives of A, I'm thinking of A as sort of playing the role of f in my definition setup, and I'm thinking of all of Rn as playing the role of this open subset of Rn. All of Rn is an open subset of Rn. So does A prime exist? Does A prime of x exist for any x? How about for all x? It'll turn out it exists for all x, and then the type of thing that A prime would be is this type of thing. Right? So what is it? So I haven't proven that this thing exists, but I'm going to. Well, let's think about it. A is a linear map. If I take some x in Rn, then if A prime x exists, then what it's supposed to be is a local approximation, local near to x, a local approximation to A, which is linear. So what would be a linear approximation to an already linear map? It should probably be the map itself. Okay, but there's some shifting going on, right? Here I'm talking about a linear approximation near x. It's going to turn out not to really matter, since, well, you'll see. So this is what I claim in the end. I claim that for all x in Rn, A prime x exists and it just equals A. Meaning, this is going to end up being a constant function, which maps everything in the domain to one linear map, namely A itself. So let's prove that. So here we have A linear map. Then let's look at the limit as h goes to 0 of ax minus ax plus h minus ax minus, and then whatever I put in this box, whatever I put in this red box is what I claim is going to be the derivative of, so this will be what I claim is A prime x, and then that linear map I'm going to feed into it h, and I should get 0. So if I can prove this about a particular thing filled in to the red box, then that thing in the red box will deserve the name A prime of x. And what I claim is that it is A itself. That's what I claim is A prime x. So can we prove this limit statement? Well, A is linear, so the numerator there is ax plus ah minus ax minus ah is 0. The numerator is 0, so yes, in fact, this is correct. This limit is 0. So indeed, A is A prime x. So if A is a linear map, Rn to Rm, then the linear approximation to A is A. The derivative of A is a constant function that maps every vector, that maps every point in the domain to A itself. Let me try to relate this to some familiar ideas for a moment. So in the early days of calculus, you might define a function. You might call this a linear map. F from R to R, given by fx equals mx, maybe mx plus b, but let's stick to strictly linear in the sense of vector spaces. Something like that, right? You'd say this has, for its graph, a line of slope m. Then what's the derivative is a constant function that constantly takes the value m, where m is a real number. That was the old way of doing things. Now the way we interpret things is not just that m is a real number, but that m is a map that multiplies things by that real number. And we're seeing the same thing. If you have a linear map, a from Rn to Rm, then its derivative is a constant function, taking the constant value, which is a itself. In our new viewpoint, we wouldn't put m here, but we would put instead the thing that maps x to mx, right? That's what f prime of x would be. In our new viewpoint, instead of f prime of x being a real number, it would be a map of this type. Okay, so just like before, we get that the derivative of a linear map is a constant function, and if you evaluate it at any point, you kind of have this, I think, pretty statement that the derivative of a linear map at a point is the original linear map.